Welcome back, scholars. In today's video, we're going to begin looking at the various factoring techniques that can be used to solve polynomial equations of the form p of x equals 0. Today, we'll focus on finding and factoring out the GCF, as well as grouping. Let's get started. We'll begin by looking over here on the left, where I have a 3-term polynomial of degree 3. I see that the equation is set equal to 0, so I'm going to be looking for the values of x that make this equation true. In other words, what values of x make this left-hand expression equal to 0? Since the degree of the polynomial is 3, from the fundamental theorem of algebra, I know this means that I have a total of 3 zeros or roots, but they may not be unique. That total of 3 includes the multiplicities of each 0. Let's start by recognizing that all 3 terms have a common factor of x, that's highlighted in blue. So I'll factor out that x, and I have the polynomial x squared minus 5x minus 6 remaining in parentheses. Let's go ahead and factor this quadratic the same way that we have previously. We'll look for 2 numbers that multiply to give negative 6 and add to give negative 5. That will be negative 6 and positive 1. So in factored form, I have x times x minus 6 times x plus 1 equals 0. Using my zero product property, I'll inspect these factors and find that when x equals 0, x equals 6, and when x equals negative 1, my equation will be equal to 0. So these are my 3 solutions to this polynomial equation. Let's look over on the right now. This time, I see that my equation is not set equal to 0, so I'll go ahead and collect all my like terms on the left-hand side. Now I'll look for any common factors. This time I have 2x. After factoring out the 2x, left over in parentheses, I have x squared minus 16x plus 64. I'll factor this quadratic using the same approach as last time. I need a pair of factors whose product is 64 and whose sum is negative 16. That will be negative 8 and negative 8. I can write this showing the x minus 8 factor squared since it has a multiplicity of 2. Once again, using my zero product property, I can see that x equals 0 and x equals 8 are my 2 solutions. This time, my 3rd degree polynomial only has 2 unique roots, but note the multiplicity of 8 is 2, so I still have a total of 3 roots corresponding to the degree of 3. Recall that the fundamental theorem of algebra takes into account the multiplicity of each root. Let's look at example 3, where we'll use grouping. Grouping is a great strategy to consider if you're working with a polynomial of 4 terms. What we're going to do here is start by looking for a GCF. Since there's none, we'll instead pair my first and second terms and third and fourth terms together and look for a GCF within each pair. In my first pair, I can factor out x squared, leaving an x plus 4 in parentheses. In my second pair, I can factor out a 2, leaving an x plus 4 in parentheses again. Notice that the expression in parentheses matches for both groups. In other words, I found a GCF for the entire expression. Using the distributive property, I can rearrange this expression. Note that my grouped expression is equivalent to x squared plus 2 times x plus 4. Now, from here, I'll use the zero product property to find my solutions. I'll have x equals negative 4 and x equals positive and negative I times the square root of 2. Remember, those imaginary roots always come in conjugate pairs. I have a total of 3 roots here, and by the fundamental theorem of algebra, a polynomial of degree 3 will have exactly that many roots. Let's look at one more. This time, I'll need to start by setting my equation equal to 0. I'll subtract 24x from both sides of the equation to do that. Next, I'm going to look for any common factors across all 4 terms. They all have an x in common, so I'll factor out an x. Next, I notice that I have 4 terms, so I may be able to factor by grouping here. I'll pair up my first 2 and second 2 terms and look for any common factors within each group. In my first group, I have a common factor of x squared. In my second grouping, I have a common factor of 4. Left over from each group, I have the expression 5x plus 6. So I'll rewrite the left-hand side of my equation in factored form. I have x times x squared minus 4 times 5x plus 6. This x squared minus 4 is a difference of 2 squares, so I'll go ahead and expand that out as x plus 2 times x minus 2. Now I'll use my zero product property to find each of my roots. I have x equals 0, x equals negative 2, x equals 2, and x equals negative 6/5. That's a total of 4 roots for a polynomial of degree 4, so I did find them all. That wraps up our first look at factoring to solve polynomial equations. Next time, we'll look at additional techniques including substitution and some special polynomial identities which can also be used to factor and solve polynomials. See you next time.